This continues the lecture covering the problems associated with the one-dimensional elastic collision. In the first example that I did in the previous video, one of the objects was initially at rest and the other object was initially moving to the right at a speed of 1 meter per second. And then ultimately this object here ended up at rest and this object here ended up at 1 meter per second. That is like so. That's the easiest situation to examine involving the one-dimensional elastic collision. In the second and third parts of this problem that we're working through, we will basically increasingly make the situation a little bit more complicated. Okay, so the second scenario is as follows. In this case, the objects are still of equal mass. The first object has an initial speed of 1 meter per second to the right-hand side, we'll say, and then the second object is initially moving towards the first at a speed of 2 meters per second. So it's a head-on collision where the objects are headed towards each other. Take a moment to copy down part B for this problem into your notes, and then let's go ahead and set it up and solve it here. Okay, so the situation is as follows. Once again, we have here a mass m, we'll say, and then an initial velocity to the right-hand side of 1 meter per second. But then right here is the second object, also of mass m, but this guy's initially moving to the left at 2 meters per second. However, I'm going to have to write the initial velocity here as a negative number, because keep in mind that these are velocity vectors, these are not speeds. And now the two objects will bounce off of each other in some manner. The first object will have an unknown final velocity v1 final. The second object will have an unknown final velocity v2 final. And then basically what we do is we set up our two equations and two unknowns, and away we go with the algebra. So let's go ahead and first of all set up the conservation of momentum expression. So change in momentum of number 1 plus change in momentum of number 2 is equal to 0, and then let's just go ahead and start to fill in our terms. So the final momentum of the first object is m times v1 final. Okay, minus then the initial, which is m times v1 naught. And then for the second object, we have the final momentum m times v2 final, and then minus the initial, which is not 0 in this example. Keep in mind that the second object is initially moving as well. So right off the bat, our expression is a little bit more complicated than it was in the previous example in the previous video. Okay, let me go ahead, however, at this point and cancel out the mass m like so. And then when you get to this point here, you want to start to simplify the problem as much as possible. You want to make the algebra that follows as easy as possible. So I didn't do this in part A of the problem, but I will do so here. At this point, I'm going to go ahead and I'm going to start filling in the numbers that were given for the initial velocities. Just be careful of your negative signs as you work. So I'm going to have here, first of all, v1 final. And then minus 1 plus v2 final, plus v2 final, and then minus a negative 2. So once again, as I said earlier, please be careful of your negative signs. So if we now do the math here, I'm going to have first of all v1 final plus v2 final, but then I have here minus 1 plus 2 for a total of plus 1, like so. And I basically simplify the equation as far as I can by plugging in my numbers. Okay, we'll do the same thing now with the elastic approximation, which is the conservation of kinetic energy equation. So now we have 0 equals delta K1 plus delta K2, and then once again we just start filling in our terms. So first of all, the final kinetic energy of number 1 half m v1 final squared, minus the initial up here before the collision, 1 half m v1 naught squared, and then the change in kinetic energy of object number 2. So final kinetic energy here after the collision, 1 half m v2 final squared, and then minus the initial, which is once again not 0, but 1 half m v2 naught squared, like so, and then equals 0. Okay, once again, you want to start simplifying the expression as much as possible. The 1 half cancels out. It always does when talking about the elastic collision. In fact, with enough experience, you frankly don't even bother writing it down. Well, let's go ahead and cancel out the 1 half. Okay, the masses are equal to each other, so let's go ahead and cancel out the masses as well, like so. And then we want to start to clean up the expression, and as we do, we're going to go ahead and start plugging in our numbers. So let me do that up here towards the top of the board. I have, first of all, v1 final squared, okay, and then minus quantity 1 squared, like so, then plus v2 final squared, and then be really careful here, minus quantity negative 2 squared equals 0 on the right-hand side, like so. Okay, now I'm going to simplify this expression some more, of course. Before I do, at this point, let me go ahead and do some erasing here. Let's get rid of all of this stuff that we don't need at this point. And now, right here, let's go ahead and get our second expression. So I'm going to have here V1 final squared plus V2 final squared. Let's write those guys first. Like so. And I'm going to have here a minus 1, but take a look at this. Negative 2 squared is 4, so then minus 4. So minus 1 minus 4 is a total of minus 5, like so. And right there now are my two equations and two unknowns, and then we run through the algebra. At this point, there's really no way around that. You just have to gut your way through it. Okay, so let's go ahead and do this on the lower board. I'm going to take this expression here and solve for V1 final. So take these two terms here and move them to the right-hand side first. That then looks like this. And then I'll take this expression here for V1 final, and I have to plug it in here and square it. Okay, so V1 final squared. So V1 final multiplied by itself. And then I have the other two terms, plus V2 final squared minus 5 is equal to 0. Okay, let's go ahead and FOIL this out. So this multiplied by this is V2 final squared. Okay, be careful of the negative signs. Multiply these guys, you get a V2 final. Multiply these guys, you get another V2 final. Like so. And then minus 1 times minus 1 is plus 1, and then the other terms. So, and then we start to simplify. When you're given a problem such as this with easy integer numbers to work with, usually by the time that you get to this point and you go a little bit further, you'll end up with a quadratic that could usually be factored. Okay, not always, but in most cases with simple problems involving simple integers, you do end up with something that's factorable. Well, let's go ahead and get there first. So let's add these guys here together. And then I have this term. And then be careful, plus 1 minus 5 is a minus 4, like so. Let's simplify even further. Let's go ahead and cancel out a 2 from each term. And when I cancel out my 2, I get this, and now let's go ahead and factor this. As I said, by the time you get to this point, you usually end up with something that's factorable. Now here's something that can help you factor. You already know ahead of time what one of the solutions has to be. Not 0, but one of the solutions has to be the no collision solution. So one of the solutions for V2 final has to be negative 2 meters per second. So then therefore, knowing that, one of my factors has to be this. Like so, because this right here would be the no collision solution. Therefore, the other factor in this example, pretty obviously, is the following. And now let's just go ahead and check. So V2 final multiplied by itself is this. Then I've got here V2 final and then a minus 1, and then plus a 2 V2 final, which is a positive V2 final like so. And then 2 times negative 1 is negative 2. So it works. We did the problem correctly, and this right here is the no collision solution. Okay, as I've already mentioned, make sure that you always look for the no collision solution. It should always be there. So then therefore, if you don't see it in your algebra, this then means that you made a mistake somewhere. You missed a negative sign or something like that. Okay, other than that, however, we don't really care about that. So let's go ahead now and finish this portion of the example. We'll do so by taking this factor here. This is the one that we want. It will set it equal to 0. And now let's go ahead and solve for the V2 final. And pretty obviously, the V2 final then ends up being a positive 1 meter per second. Notice that the final velocity of number 2 is the same as the initial velocity of number 1. And now right here, let's go ahead and find the V1 final. So V1 final is equal to negative V2 final minus 1, negative 2 meters per second. Notice that the final velocity of number 1 is the same as the initial velocity of number 2. What this means is that the objects have exchanged velocities. This will always happen as long as the objects are of equal mass. This always occurs if the objects are of equal mass. That actually also occurred in part A of the problem, but I didn't say it as such in that video during that lecture. But recall what happened in part A of this example. The carts here have the same mass. This object was initially at rest. This object was initially moving in that direction at 1 meter per second. And then this object ends up at rest, and this object here ends up at 1 meter per second in that direction. The objects exchanged velocities. Same thing here now in part B of the problem. So then therefore, here's how I'll set this up. This guy here, object number 1, is initially moving that way at 1 meter per second. This guy here, object number 2, is initially moving that way at 2 meters per second. And then they bounce off of each other. This guy rebounds that way at 1 meter per second. This guy rebounds that way at 2 meters per second. So here's how I'm going to demonstrate it. This guy, I'll say, is initially moving slowly. This guy is initially moving quickly. So then watch what happens when I do this. This guy ends up quickly in that direction, and this guy ends up slowly in that direction. The objects have exchanged velocities. They always will do so as long as the masses are equal. Now there is a part C to this problem involving unequal masses. I'll do that in the next film.